Hey everybody, and welcome to another episode of Space Science with Python. Last time we created this plot. It shows the velocity of our impacting dust particles versus the rise time and the amplitude. And you see the dots, they are the calibration data, and this plane is based on a calibration fitting using TensorFlow and the Keras API. And it was quite a nice visualization to show how this training or the final product or model looked like. And we used a very simple model, and we didn't conducted any best practices here. We just wanted to have a small first overview. Today we are going to consider a little bit also the distribution of the data points, because you see in the plot that some data are some regions are denser, some regions are more sparse, and if you do a naive splitting of the training and testing data, you may neglect certain areas, which leads then to a severe bias in the fitting process. And this is something we will do today. And further, I would like to note that all the scripts you see here are in the GitHub repository, and the link is in the description. So there you can see all the other scripts as well, also from all other tutorials. So feel free to fork it, to give it a star, and to use it for your own needs. And well, I would suggest let's dive into the data. Let's see what we can do today. And don't miss also the Outlook, because in the Outlook we will also talk a little bit what we are going to do next. Okay, let's dive into the coding. First of all, again, the script is divided into the different sections, and the different sections correspond to the timestamp you see at the bottom in the description. So you can skip certain parts if you're not interested. For example, the very first part, read in the data, is something we already did thousands of times. So I skipped this part here. We have the QI/IED data, and here we have the overall distribution. Now what we need is, if we want to have some sampling weight, we need to first of all have a look at the distribution of our data. Let's do this here. And what we see is here, for example, the rise time, the amplitude distribution, and the PSU velocity in kilometers per second. And what we need now is we need to split the training, the testing, and the validation in a way that this distribution over all three parts is preserved. So we have to do this in our next part, the calibration weighting. And the weighting is quite straightforward. We have to define our histogram, our bins. And these are the bins I just defined. So for the velocity, the rise time, and the amplitude. Again, histograms are, you can also, Bayesian blocks would be better, but I will talk about this in a future video. So let's simply execute this here. And if we want to do the sampling weighting, we have to consider one thing. We have here, for example, the distribution of the QI amplitudes. And we see here we have only 4 entries between minus 0.5 and 0 femtocoulomb, or log 10 femtocoulomb. So we have to take care that we only have 4 values, and we need to, in a way, oversample this. Here we have like around 600, so we have to undersample this in a way. And how do we do that? Well, first of all, we take the array, we divide it by the sum of the entire array, and then invert it, so that this value becomes larger and this value becomes smaller. And now we can use these entries, the entry values, and we can assign this weight now to the corresponding velocity, rise time, and amplitude in our data frame. And how do we do that? Well, simply with a numpy where function, where we say, okay, let's take an example here in the rise time. If we have like the rise time is between 0 and 10 microseconds, then this condition leads to it checks where the very first difference is larger than 0. So for example, it would be the very first entry, and takes then the first argument, which is then the 0th entry, and puts it into the entries array. So what happens is we get this value 4, or let's say divided by the sum and the 1. So maybe we should just print out the value here, for example, for the rise time. So this is now the value 41 that is now added here if our rise time is between 0 and 10 microseconds. If it's between 0 and between 10 and 20 microseconds, then the first entry will be negative and the next one will be positive, so larger than 0. The other ones will also be positive, but with a larger difference. But again, we only take the smallest argument and then put this argument as an input to the sampling weight array. If it's a little bit too complicated, just print out the values. I think this helps to understand what really happens here. So let's execute this command here. We only consider the values we are interested in. And then we can conduct our training test validation splitting. And this splitting is also quite straightforward. We use again this train test split method. And first of all, we need to add a new not value, but a new parameter, namely stratify. And stratify considers this weight distribution. So we use this value here and we say that we would like to have a test set of 20%. Now we get the test set here afterwards, but now we have this, I call it pre-train, yeah? And the pre-train is again splitted into training and validation, because in Keras we can simply provide the ratio for the validation splitting, but it does not consider, for example, a sampling weight or so. So we do this also here manually in this cell, where we use the pre-train values and then simply split it up into a training and validation of 25% respective to the already splitted data. So at the end we have 60% training, 20% validation, 20% testing. And now we can plot the distributions again for all our cases. And what we see here is that the distribution is almost preserved, right? So the training data is in colored, is black colored or gray. Validation is blue and test is red. So the color combination would be like a magenta, and you see a lot of magenta here. So they have almost the same distribution because 20%. And yeah, for certain extreme values, like here you see in the training, we do not have really data, but this is just because of the lack of data. But yeah, with the eye, you see our distribution is preserved. Now we can do the scaling. Again, I skipped this part here because we already did that. And then we can conduct our machine learning training. The same method as last time, just with two more additions. The first one is that we add now an early stopping. So if the validation loss reaches a minimum, yeah, after 25 epochs, it does not improve, we stop our training, we have the best validation minimum, and then we restore the model with the best weights at that point. So this is the one thing we add. And the second thing is here, the validation data is now provided as a tuple. So we really use now our scaled validation and scaled velocity data as an input for the model, and we do not provide any ratio or something like that. So we can execute that here, and it just takes some minutes, and just a few seconds, and yeah, we know it's finished when we get our validation and loss function. And again, we will do a k-fold in the future, so we will not bias our training with only one with the same validation set all over again. So let's wait for a few seconds. And there we see the loss and the validation loss. At some point, yeah, maybe afterwards, the validation loss increases again. And here's like probably somewhere the minimum case. So yeah, again, let's show our model for this remnant from last time. And what we can do is now to plot the RMSE and the mean absolute error, and it's around 14 and 12 kilometers per second respectively. Again, we can also show our plot like we did last time in the 3D plot using matplotlib, which is quite slow. So we will also do some introduce some plotting routines that are more powerful than that. And here you see the final plane where the round dots are our training data, I guess, was it? Yeah, and the squares are our test data, and here you see the distribution all over again. So yeah, it fits quite nicely. I don't know if we can really improve this one here. I mean, the deviation, the RMSE is really inherently given by the test data. So it's nothing we can really work on or improve. The data are as we have it. So that's basically it, right? But what is the outlook? Well, the outlook, I told you, K-fold, I told you also with the Keras Hyper Tuner. Maybe it's a little bit overkill for this project, but it is something, some methods you learn. And also what's interesting is this RMSE value you have seen here. This is the value that applies for all test data. But if you take a look, you see maybe the values here are a little bit better than, for example, in this region. And this is also something we will do in the future, where we will evaluate our model depending on the position of the model, right? So for example, we can, if you take a look here for values smaller than 10 microseconds, then we have a larger mean absolute error compared to, for example, larger than, let's take 80 microseconds. Then we have 10 kilometers per second, which is an improvement. So yeah, our error really deviates or depends on the location of the model. And this is something we will also consider in our future video. So this was our small coding example today. And as you've seen in the Outlook, it would be quite nice to see the varying RMSE values, so the errors for different regions of the plot. I don't know if we will do this now for our two-dimensional plot, because the 2D calibration plane, the metrics, they are not really an improvement compared to the original function. So let's wait maybe here for another session. But what we can do to improve or introduce more best practices is to also first of all introduce a K-fold training process, so that we split our training and validation testing data set, for example, 5 times, shuffling it 5 times, and so that we obtain better statistics of our metrics. This would be the one thing. And the other thing is also maybe to improve also our neural network a little bit, and yeah, provide some kind of tuning mechanism to cover a larger solution space for potential neural networks. So for example, we can use Keras Tuner to cover larger potential solution spaces and play around with more architectures. But as you've seen in the plot looks already quite nice, right? I don't think we can really improve it even more. So what we will do is introducing more best practices, but this won't really improve the RMSE or the mean absolute error, which is, I think, okay. So let's focus on the best practices first. Additionally, we can also introduce more features into our calibration. So for example, we use the data of one channel. We can now add the data from other channels as well. Like for example, the particle hits the target and some ions fly to another channel or so, and then we can also use these data for calibration. But this is something I will only show in one video to see if we get a data improvement or not. And then at the very end, I would like to go back to our original calibration in simple 2D. So on the x-axis the rise time, on the y-axis the velocity, and conduct also here a regression curve or regression task by also doing some sample weighting, but not using any predefined bins, but introducing Bayesian blocks. And what are Bayesian blocks? Well, I would say we will cover this in the future video. So next time, let's introduce Keras Tuner and the K-fold part to improve our best practices. Then we will add more features into our regression, and then we will finalize everything with the original regression curve. And then we are finished with this regression project, and then we can go into the next projects and the next steps. As always, thanks for watching.